Before moving to the problem of DFT, two things have to be considered here. The first one is the zero padding, and the second thing is the properties of the twiddle factor. We can consider what is twiddle factor, and before going to twiddle factor, we are going to consider the zero padding. What is zero padding? Here, let this be a signal in which we have to do the DFT, in which this is a discrete signal x of n, which is having a number of elements, a 9 number of elements are here, that is the 9 samples are here in the x of n. And we have learned earlier that the DFT is the sampled form of DTFT, that is we are taking in the case of the endpoint DFT, we are taking the n samples of the DTFT continuous frequency domain signals. Let x of e raised to j omega be the DTFT, and we are taking n samples, so the sampling interval which is given by 2 pi by n. And we have told that the number of the sampling points, the n, should always be greater than or equal to the length of the samples. That is, if the L length is equal to 9, then the n should be greater than or equal to the n should be greater than, the number of sampling points should be greater than or equal to the number of the samples in the time domain, the discrete time domain signal. Then here it says why we should take that. Here this is the XPN. XPN is the discrete signal of the DTFT, that is the sampled signal of the DTFT, that is this shows a DFT. We can simply say this is the DFT of the x of n. Then we have taken the n samples of the DTFT, which gives the DFT of this, and as the n is greater than L, we can see we have obtained the spectrum individually without any loss, that is the whole spectrum is obtained. Then there is a small gap in here, and then we have obtained the periodic form of the discrete frequency domain spectrum of the x of n here. But here let us consider if n is less than L. Here the n is less than L here. Then here we can see that the overlapping occurred here, that is one before the end of one whole spectrum, the other spectrum started to appear. So the overlapping occurred here. So between this and this we have lost some of the signals, or some of the datas have been lost here. So overlapping occurred here, aliasing occurred here, and this loss happened when the number of the sampling point is less than L. So one thing we should consider when doing the DFT is that the n should be made greater than or equal to L. The common procedure we are doing is that the n which is kept equal to the L, that is the number of sampling points is kept nearly equal to the length of the sequence. Let the x of n is equal to a sequence 1 2 3 which contains 3 elements, that is L is equal to 3 elements are here, and the n is equal to 5. Then what we have to do is we have to add the n minus L zeros to the end of the sequence, that is the sequence now becomes 1 2 3, and at the end of the sequence we have to add n minus L zeros, that is 5 minus 3 is equal to 2 zeros has to be added, 0 0. So the sequence now becomes an element of 5 which is equal to the n. So if we do this, we can avoid the problem of this overlapping, and the signal loss can be eliminated, and we can simply do the DFT, and we can obtain the DFT without any loss. And this process of adding the n minus l zeros to a sequence or under consideration, which is called zero padding. So this helps to avoid any aliasing error which can occur in the case of doing the DFT problems when taking n samples of the DTFT from the to obtain the DFT. Okay, this is one thing which we should consider. The n should be greater than l, and the zero padding, the addition of n minus l zeros to a sequence. So if we have a sequence of 9 elements, and we are supposed to find the n point DFT where n is equal to 10, then we have to add n minus l zeros, that is 10 minus 9 is equal to 1 0 has to be added to the end of the sequence to make the sequence l is equal to n, and this is called zero padding. The next thing is, we have told the DFT of the sequence is given by this, and the term e raised to minus j 2 pi by n into kn is written as omega n, which is equal to e raised to minus j 2 pi by n. So the term e raised to minus 2 pi by n kn, which is written as omega n raised to kn, and this is called as Tudel factor or phase factor, because this term which determines the phase of the phase of the sequence we are obtaining. And so this is called Tudel factor, and there is some properties of this Tudel factor, and we know that we are giving a periodic signal, discrete time signal, as the input of the DFT, and what we are getting is the discrete periodic frequency domain signal, and this conversion from the aperiodic to periodic frequency domain signal is done by the Tudel factor. And here we can see that the two properties of Tudel factor is periodicity and symmetricity. Here we can see that if we are having the n point DFT for let n is equal to 4, then we can divide this circle as 4, and this given by omega 4 raised to 0 omega, then the direction of rotation is omega 4 raised to 0, omega 4 raised to 1, omega 4 raised to 2, and omega 4 raised to 3. Then after this point, again it is repeating, like what we have told in the that is this output spectrum we are obtaining, and after n, then the value of 0 which is equal to n, and that is then again it is again repeating, and the spectrum is repeating, and this repetition of the spectrum and the periodicity is obtained due to this Tudel factor. So if we have to find the values, we only have then certain values are equal, that is omega 4 is 0 and omega 4 raised to 4, which is equal to 1, and the periodicity. And the symmetry is that then the omega 4 raised to 0, then when adding the half of the n, that is n by 4 is added to the exponential term as exponential, then omega 4 raised to 0, which is equal to omega negative of omega 4 raised to 2. That is we can simply say omega r is equal to minus of omega r raised to n plus 2. That is omega 4 raised to 0 is equal to the negative then omega 4 raised to 0 is equal to omega minus of omega 4 raised to 2. That is the negative value of this is given by this. That is the symmetric property, and the periodicity property which is given by omega raised to r, which is equal to omega raised to r plus n, which is given by the periodic property. That is the value will repeat.